Okay, we're going to get into the math portion of Chapter 8, talking about the heat requirements needed to overcome some of these intermolecular forces. And we're going to focus on heating curves for water for now, but we can do this with any substance. Water is just one that we're really familiar with, so you can see how to draw these. And the temperature over here is on the right, or on the left-hand side. And it goes from negative 20 to 0 degrees. And we know that at 0 degrees, water melts. So we're starting out with solid ice, and then we're melting the ice. And it'll stay at 0 degrees. That's a really important point, until all of the ice actually melts. The liquid water cannot heat up while the ice is there, because the ice needs to absorb all the energy. And then it goes, liquid heats up to 100, and then we get it to boil. And there's energy being added, x-axis, but the temperature does not change. So this is where the actual intermolecular forces are being broken, at the melting point and the boiling point. The solid, liquid, gas portions, those heating curves, are actually MCAT equations. It's just how much energy is it absorbing based on its specific heat. Now you will notice here that these curves, or these slopes have different, the solid, liquid, and gas have different slopes. And that's because they have different heat capacities. Now this isn't totally drawn to scale, because there's an energy axis down here on the bottom. We'll call this kilojoules. So not totally accurate here. But you can see what should happen is the slopes of the graph is how quickly it changes. In general, if we were to say it has a really steep slope, it's changing temperature very quickly, and that would be easy to change, so we would call this a low heat capacity. Versus something that's very gradual, takes a lot of energy to change. This would be a higher heat capacity. And this graph, being not to scale, has them actually totally backwards. And we can see that here. This is just some data that you have for water. So you're given this stuff in different problems. Specific heat of ice versus liquid water, 4.2, 4.18, water vapor. So the first thing we know is that solid, liquid, and gas. Water does not have a specific heat of 4.18 all the time. Only liquid water does, which is what we use for calorimetry. Sometimes if it's a solid, it's 2.1. Ice absorbs heat at a different capacity than liquid. Ice doesn't take as much energy to change the temperature. And then the water vapor, being 1.8, is really easy, changes temperature very quickly, being 1.8. And then at the melting and boiling point, we get the heat of fusion and the heat of vaporization. Now vaporization you're familiar with, that is liquid to gas. Fusion is probably not one you've heard apart from nuclear fusion, but that is just our solid to liquid melting boundary. Kilojoules per mole, kilojoules per mole. Ignoring the formatting here, this is just, and I wouldn't memorize this equation because it's just a stoichiometry problem. Moles times the heat capacity. The moles will cancel out, you'll get energy. And then this one over here didn't format too well either, but this is just our MCAT equation if we have the heat capacity. So we've just got to combine these two equations. When I have a solid, liquid, or a gas, we use this to see how much energy it absorbs. But when we're trying to figure out how much energy to break the intermolecular forces, we have a stoichiometry problem over here. Let's see what that looks like. How much energy does it take to convert 130 grams of ice at negative 40 degrees Celsius, it's not 400, to steam at 160 degrees Celsius. So here we go. Let's kind of draw our curve first. We start at negative 40. Now since this is water, we know that it's going to 0. And then it'll melt. And then it's going to go up to 100. And we're not trying to draw the slopes totally to scale. And then it'll boil. And then we need to go up to 160. Okay. So there's 5 different energy changes going on here. I've got heat here of the ice. I've got heat here of the fusion, which is the melting. Heat of the liquid. I've got heat of the vaporization process. And then I've got heat of the gas. So what we need to do is just add all of those quantities up. We have to calculate 5 separate things, add them up, pay attention to units and sig figs. And it's really a simple problem, but it's tedious in that you're doing 5 different calculations. So let's get that curve going. The first one, we have the heat of ice, which is from negative 40 to 0. Now, in all of these processes, since we're separating the particles from solid to liquid to gas and melting and boiling, we're giving them more energy. Energy is going in, endothermic. All of these values are going to come out positive. If you pay attention to the math, they're all going to do that anyway, but if you mess up, they should be positive, so you can just kind of logically think through that. So here we go. The first one, the mass is 130 grams. The specific heat of ice we looked up from the last slide is 2.18 joules per gram per degree Celsius. And we are changing it, final minus initial, 0 minus 40. We are changing the temperature 40 degrees Celsius, which will be 10,920 joules. Now we have the heat of fusion, which is melting the ice, which depends on how much ice we have. So 130 grams of water. Okay. Since our heat of fusion is given in grams per mole, we need to know how many moles we have. 18.02 kilojoules per mole. Then our heat of fusion is 1 mole is 6.0 kilojoules. So 43 kilojoules. Now right there we see we have a problem. Our first heat gave us joules, our second one gave us kilojoules. If we round this first one to sig figs, we're at 11 kilojoules. Okay, because we're going to need to match later. Then we have liquid. So, and we're going from 0 to 100 degrees. So 130 grams, we're just heating it up, 4.18, because that's the liquid. And then we're changing it 100 degrees. Now water always goes 0 and 100. If you have something that melts at 20 degrees and boils at 50, you need to adjust your heating curve accordingly. So this one's going to be 54 kilojoules. And then we have our heat of vaporization. So same, it's in kilojoules per mole. We need to know how many moles we have. 18.02 grams of water for 1 mole. And now this specific heat is, this heat capacity, that's still not right. The heat of vaporization, 43.9 kilojoules. That is huge. Gives us 317 kilojoules. Let's pause here, because you can always look at energy requirements to tell you about the strength of these intermolecular forces. My fusion was 6 kilojoules per mole. My vaporization was much, much, much higher, 44 kilojoules per mole. Why does it take more energy to vaporize it than it does to this one? Well, because this is going from a solid to a liquid, which just requires a little bit of movement. But this is going from a liquid to a gas, which totally requires you to break all the intermolecular forces and get every single particle by itself. So just the energy requirements alone, they always tell you how easy and difficult things are and how strong the forces are. If you had another substance that required 50 kilojoules to break, you would know that that substance had stronger forces to overcome because it takes more energy. So these things are always related. Last one is the gas. We're going from 100 degrees where it boiled to, I think this one stopped at 160. So 130 grams. The specific heat of the gas is 1.8 joules per gram per degree. And this is going to be 60 degree change for a total of 14 kilojoules. Okay, we add all of these guys up. And we get our grand total. It takes 439 kilojoules of energy to take ice, 130 grams of ice, and turn it into steam at 160 degrees.